Hello. So today we'll discuss on the contents of module 10, which will be on X-ray diffraction. So in the previous module 2, we had started on X-ray diffraction. I'll quickly go through the topics which we discussed. So we started with compositional analysis techniques. So we can do it using BSE signal and SEM, that is backscattered electrons. Then X-ray generation was covered. So what is an X-ray? Some of the basic terms that you need to know. So then we looked at how the X-ray spectrum usually looks. It's a continuous spectrum with some peaks, which are the characteristic X-rays. Then we looked at characteristic X-rays in particular and how they are produced. Then we also discussed how we can identify, how we can describe each of them, or the terms we use to describe different kinds of characteristic X-rays. For example, K alpha, L alpha, K beta. Then we looked at production of X-rays, how X-rays are produced. We do it using X-ray tubes in usually, and then we look at how X-rays interact with the particular. We looked at mass absorption coefficient, how much of the incident X-ray is getting absorbed by the material, some characteristics of mass absorption coefficient. After that, we discussed the mm, mass absorption coefficient dependence on the wavelength and what is absorption edge. Then we also touched upon OJ electrons and OJ effect, which is an alternate route to generation, which is an alternate path that can take place when you're trying to generate X-rays. So either you can generate X-rays or you can generate some OJ electrons. Both are possible. That was what we covered in the previous module. This time we'll continue from there. We'll again look at X-ray absorption, some filters. Then we'll talk in more detail on the intensity of diffracted X-rays, and because diffraction is going to be very uh, important due to the applications that make use of X-ray diffraction phenomenon. So we look in detail at diffraction and what are the factors that affect the intensity of the diffracted beam. So if we have a material and X-ray is incident on it, then we already discussed that part of the incident X-rays will get absorbed. It might get scattered or undergo some other interactions with the specimen. And if we try to look at how the energy of the X-ray affects the mass absorption coefficient. So the dependence is something like this. At high wavelength, that is low energy, the mass absorption will be higher because low energy X-rays can easily get scattered. But as the energy of the X-rays increases, it's less likely that the mm, beam will get scattered, and this is because it's less likely that there will be interaction with the scattering center mm, since the energy of the beam is so high, that is the wavelength is very small. So now we know that in general we'll see this kind of a decreasing trend as the energy increases. But what we observe is that below a particular wavelength, there is a sudden increase in the mass absorption coefficient, and we usually call it an absorption edge. And the reason this absorption edge forms is that uh, ahead of this uh, absorption edge, the energy of the X-ray is not high enough to be able to knock out inertial electron. So the only loss of X-ray beam energy or only absorption occurs by scattering by the atoms and the electrons of the atoms. But once the energy is high enough to knock out the inertial electrons, then a larger portion of the incident X-rays gets utilized in that only in removing the inertial electrons, and as a result, we see a sudden increase in the absorption of the X-ray. And the wavelength below which this occurs is called the K absorption edge. Mm, yeah. This is the formula for no, for the relationship between the transmitted beam intensity and the mass absorption coefficient. Similar to the K absorption, which may be somewhere here, KH, you can also have other absorption edges like L1, 2, 3 are, I think, for the different orbitals within the L shell, and we can also have M edges similarly. So L basically refers to the second shell, M refers to the third shell. And now that we know the relationship between the absorption edge and the wavelength, we can also relate it to the atomic number of the specimen. So we know that the energy required to remove an electron from atom atom at ground state is dependent on the atomic number of the atom, because the atomic number decides the positive charge of the nuclei. The higher the atomic number, the more positively charged the nuclei is, and the more is the uh, binding energy of the electrons. So it is understandable that as the atomic number increases, more X-rays of higher energies are required to knock out the electrons, and as a result, the absorption edge will change as you uh, change the atomic number of the specimen. So one practical use of the absorption edge is that by experimentally seeing what are the wavelengths at which the absorption edges are occurring, we can get a sense of the energy levels of the atom for different cases. For example, mm, what is the energy level associated with removal of a electron from a K shell or from a L shell? That we can get from knowing the energies associated with K absorption edge and L absorption edge. So this is the describing. So the neutral atom is at ground state. If you remove an electron, then the potential energy of the atom increases. That is, you had to do some work to remove that electron from away from the atom. So the energy of the atom has increased. And if you remove it from the K state, the new energy will be somewhere here. But after this excitation, if there is electron coming from the L state to the K state, then there will be a decrease in the energy of the atom, and the new energy will be somewhere here. Similarly, if it's from the M shell to the K shell, it will be here, corresponding to emission of a K beta X-ray, and so on. So in this energy level diagram, you can describe all possibilities and the corresponding energy levels. So here also the same thing is being shown. The difference between the energy levels of two different uh, atomics. So the difference between two different levels, energy is corresponding to two different uh, excited atoms, you can say, or two different levels, will correspond to the energy correspond to the X-ray beam energy of the X-ray beam generated as a result of the transition between them. So if an electron moves from a L3 state or L3 level to K level, then corresponding to this change in energy of atom, there will be a X-ray that is getting generated. So basically, the atom's energy is decreasing because electron is going from higher to lower shell, and this decrease in energy of electron corresponds to generation of an X-ray during the transition, so as to balance the energies so that no energy gets created or destroyed, and this energy will correspond to h mu into h mu, where mu is the frequency of the X-ray that got generated. Here also is the same thing. So this energy K absorption H can also be related to the voltage that was applied to generate the X-rays. So because X-rays are generated again by mm, inertial excitation in X-ray tubes, so you can uh, correlate the energy of the generated X-ray with the voltage applied to the electrons in the X-ray tube. We have already discussed that before. Now we'll move to how we can separate out particular X-ray beams of particular energies so that it can be later on. So typically when you are producing X-rays, uh, you'll get a continuous X-ray spectrum with some peaks, but it is possible to reduce the energy reduce the uh, range of energies to smaller smaller values by using a filter. So basically you are removing X-rays belonging to other energies and only keeping X-ray belonging to a particular energy. For example, that can be K alpha. And to do that, we have to select a filter material in such a way that it will absorb all the X-rays which are of energies which we do not desire, while retaining the X-rays of a particular energy value. So this is typically done by taking a material having one atomic number less than that of the target metal from which the X-ray was generated, because we know that as you decrease the atomic number, like go to lower atomic numbers, the energy required to remove k electrons also reduces, since the binding energy is reducing. So if the filter material has an atomic number one less than target metal, then usually uh, the filter material will be able to absorb some of the X-rays coming from the target material. For example, in this case, we have a nickel filter, or I think a copper target, and the K absorption edge of nickel is just a bit lower than the K alpha of copper. So as a result, so this is the image where we should look. So as a result, all the X-rays having wavelength less than the K alpha value or less than the absorption edge will get highly absorbed, while those having wavelengths more than the absorption edge will not get absorbed to that extent. So as a result, from this kind of X-ray,
Gotcha.
excuse me, if you have any question, you can let me know. Yeah. So from this kind of X-ray absorption plot, we can get a plot which will be something like this. So initially we had K beta also as well as some background X-rays, but after putting the filter, the K beta as well background X-rays reduced and the K alpha was reduced to a much less extent. So the X-ray has become more monochromatic, that of a single wavelength after putting the filter. Yeah. So this plot also shows the same thing. So without the filter, we had two different peaks, but after putting a filter in between, like after the putting a filter above the target material, we were able to reduce the K beta peak significantly, and we only had a K alpha peak. And this has but this has multiple important applications, because typically when you want to do any kind of a diffraction experiment, we want to be working with monochromatic X-rays, that is X-rays having majorly a single wavelength, so that you can better study the diffraction and interference phenomena so as to characterize a material. That could be one use case. So this is one of, or this is actually the way in which mm, mon, the generation of monochromatic X-rays happens by using a suitable filter. Now we'll move to diffraction of X-rays. Till now we only talked about generation of X-rays and the uh, phenomena that take place at the atomic level, which lead to X-ray generation. And now that we have a good understanding of what are X-rays, we'll move to diffraction in X-rays and some other concepts related to diffracted X-ray beams. Uh, Previously talked about Bragg's law, which tells you at what values of 2 theta, that is at what angles with respect to the incident beam, we'll see diffraction of X-rays or of any electromagnetic radiation. And basically what happens is that there are particular angles at which interference, constructive interference of scattered beam takes place, and at those angles we get very high intensities. And this phenomena of getting very high intensities at certain angles is called diffraction of beams or electromagnetic radiation. I hope you all can recall what Bragg's law is. So for example, if we have a plane of atoms like this and there is an incident beam coming, uh, this plane of atoms can diffract it at a particular angle. Let's say it's this here, 2 theta, in the beam that is coming at this angle, and this is called the diffracted beam. Let me say, let me just point it out. It's this. So we already know this, but we'll again take a look at it, and also we'll try to understand how the arrangement of the atoms in a unit cell can affect the diffracted beam that is coming out. So we know that Bragg's particular angle, but there is another aspect to Bragg's law, and that is that it is not necessary that if Bragg's law is getting satisfied for a particular angle, then diffraction will happen at that angle. So it can happen that atoms are arranged in such a way that there is some destructive interference taking place at that angle, even though Bragg's law is being followed, and you might not be able to see a peak in intensity at those angles. So though we have talked about Bragg's law earlier and about diffraction, we never really mm, covered in depth why diffraction occurs, or in particular, why does X-ray beam get scattered by atoms or by other scattering centers in a specimen related to diffraction phenomena. So now we'll look at this in detail. So when we have a specimen with atoms, then there will be electron clouds surrounding each atom, and effectively the scattering that occurs of the incident X-ray happens majorly by these electron clouds, and this effect of scattering by an electron is called Thomson effect. So since we know that any radiation, electromagnetic radiation, has an electric field and magnetic field associated with it. In case radiation is falling on an atom, then it will interact with the charged particles that are for example, the electrons, which are negatively charged in the atom. So the electrons will interact with the electromagnetic radiation, and due to the oscillating electric field of X-ray beam in this case, there will also be an oscillation of the electrons of the atom, and that oscillation generation of radiation, since there is a change in the acceleration of a charged particle, so some energy will be getting lost as radiation, and this energy loss due to oscillation of the electron mm, happens in such a way that the energy of the beam that is generated due to the oscillation is the same as that of the incident beam, and the wavelengths will be the same even after scattering has occurred by the electrons, but the phase will change by pi by 2, and this will happen at all angles. So the scattering won't be restricted to any one angle. Since the electron is oscillating depending on the direction of oscillation of the electric field in the radiation, so in all at all angles we'll have some scattering, and the intensity of the scattering at any angle can be given by this formula. So alpha is angle between scattering direction and direction of acceleration of electrons. So if the angle of incident and scattered beam is the same, then the angle alpha will be 90 degrees, since the oscillation is perpendicular to the direction of propagation of the beam. So I will be equal to I naught k by r square. But if alpha is equal to 0 degrees, that is the scattered beam is perpendicular to the incident beam, then you will not have any scattering in that direction, in your perpendicular direction. So if so, we know that the intensity of the beam that has scattered will be dependent on the angle at which it was scattered. So we can say that there will be a effect of the angle on the intensity of scattered beam, and this effect is quantified by polarization factor, which is given by 1 plus cos square 2 theta by 2. So this was one of the factors that will affect the intensity of the scattered beam. Now we'll look at what happens if a X-ray is incident on an electron, which is not a part of which is not strongly held by the atom. It is either loosely held or it is a free electron. So even these could be electrons which are in the valence shell, or mm, so either they could be in the valence shell, or they could be in, for example, in metals, they could be just free electrons. So these will also interact with the X-rays, and in this case, the kind of interaction will be different compared to that with an atom which is closely held by the nuclei. So in this case, the scattering that happens will lead to generation of uh, a beam, or lead to an energy generation which is slightly lower than that of the incident beam. So the X-ray which will be generated will have a slightly higher wavelength compared to the initial beam. And another thing is, the generated X-ray will not have any phase relationship with the incident beam. That is, the scattered beam will be incoherent. So this will not uh, cause any diffraction effects. In case there is any question, you can let me know. So this kind of a scattering by loosely bound or free electrons is called Crompton effect, and this also contributes to the scattered beam that we observe when we have X-rays incident on a material. We have looked at Thomson effect now, which tells what is the effect of scattering by an electron at different angles. Now, if we consider that scattering that occurs because of an atom and not just because of a single electron, then we can see that each electron be will be contributing to the scattering, and all of these different electrons, the contributions of each of these electrons can be added up so that you can get the overall scattering by an atom. Now, how can we do that? If the scattering is in the forward direction, that is along the incident beam. For example, in this plot we can see. So if it is along the incident beam, then there will be no path difference between the scattered beam from A or from B, because both these beams have traveled the same path. So they will still continue to be totally in phase, and as a result, we can just if we have a forward scattering, we can just multiply the amplitude of the scatter, which is the total number of electrons in the atom, and that will give us the amplitude of scattered beam by the atom. But in case the scattering is at some other angle, let's say 2 theta, then there will be a path difference between uh, the two different scattered beams from two electrons, and due to this path difference, the cumulative amplitude amplitude of the uh, cumulative beam, or the beam that will interfere, the beam formed by interference of these two will be different from the sum of the two individually. So what I'm essentially trying to say is that if the scattering is at an angle, you can't be adding up the amplitudes of the individual scattered beam from two different electrons. You also have to consider the phases of the two beams. So in order to consider the phase difference between the scattered beams at different angles, we have something called the atomic scattering factor to take care of this phase difference. If we want to look at the effect of uh, atom, that is scattering by an atom, on the amplitude, then we can define something which is something like this: amplitude of wave scattered by an atom with z electrons, that is by the whole atom, divided by the scattering by a single electron. And this is essentially what we are interested in, and we can denote this as atomic scattering factor. Now we know that the scattering factor will depend on the angle at which the scattering occurs, because the electrons are all at different positions in the atom. So the angle is important. And if we look at the experimental values of atomic scattering factor with respect to the angle, scattering angle, we see that at 0 degree, as expected, the scattering factor is 1. We can just add up in like scattered intensities. But as you increase it, the atomic scattering factor decreases. Also, this scattering factor will depend on the wavelength of the incident X-rays. So you can go through this PDF to understand that effect. I won't cover it now. As I had previously mentioned, uh, interference can only occur if we have coherent beam. So in case of incoherent beam, we can't just add up the amplitude because all the phase different, there will be lots of phase difference between different beams. So as a result, interference will not occur, and that happens when we have Compton effect, which we just talked about like few slides earlier.
Sir, Abhinav sir. Abhinav,
Yes, yes.
sir, your voice is a double voice, sir. Two
Uh,
times are speaking each word.
Now is it okay?
Now also same.
There is some echoing.
Maybe that not.
Okay. Are others also facing this issue? Let me just put my earphones and try. Hello.
Hello.
Hello. Now is it better? Now is my audio okay? Okay, let me continue. So I was saying that in case of Compton scattering, we'll have incoherent scattered beam, which will not contribute to diffraction. And this effect will be much more at the lower atomic numbers. So for example, for organic materials, we'll have more of the Compton scattering, while at higher atomic numbers, we'll have more of Thomson scattering because the electrons are more strongly bonded to the nuclei. Mm. So these are the different possible phenomena which can occur when an incident electromagnetic beam interacts with some material. And when we are looking at X-ray diffraction, we are majorly interested with the uh, coherent beam that gets generated, and diffraction is essentially interference of this coherent beam, which leads to reinforcement of scattering. So now if diffraction is clear to you all, we can we have already looked at scattering due to an electron as well as due to a hole of an atom. Now we'll see how scattering can occur by a unit cell which has multiple atoms placed at different positions. So we are slowly going from understanding it at a fundamental level to be able to applying it to at larger scales. That is at unit cells, at the length scale of unit cells. We already know that the mm, angles at which diffraction can occur will be governed by Fick's law. And I won't talk about the derivation of Bragg's law right now, but you can look it up if you are not sure why diffraction only occurs. Diffracted beam can only be observed at particular angles. But if the arrangement of atoms in a unit cell changes, then the intensity of the diffracted beam can also change. It can either be it can either remain the same or it can reduce. In order to understand how the arrangement of atoms mm, can affect the intensity of the diffracted beam, we can start with looking at a unit cell having these different these atoms. So these are at the corners, and then we have some other atoms at different positions. And if we have an incident X-ray beam in one and two directions which are parallel, and we have a H00 plane which is causing the diffraction, then the angle at which diffraction will occur is this 2 theta. Sorry, yeah, this is not 2 theta. Basically, the angle between the incident and diffracted beam will be 2 theta. And we know that if we just have atoms on the H00 plane, then we'll see diffracted beams 1 dash and 2 dash. But if you also have some more atoms at other positions, such as at B, which is at a fractional coordinate, it is now not at the corner of the unit cell, then diffraction can also occur due to this atomic layer here. And the value of the diffracted intensity due to presence of this atomic layer, can be found out by doing a calculation. So this is the calculation sir had done in the lecture to be able to know what will be the phase difference between the diffracted beam by this plane of the new set of atoms and these set of atoms at the lattice positions. So this is also a lattice position, but it is as at a fractional coordinate. For example, it could be this face centered position, or it could be a body centered position. So these are fractional coordinates, and there will be a phase difference between the diffracted beam from this particular plane and this particular plane, which is at fractional coordinate. And this phase difference can be given by this formula phi. For example, between the incident beam 1 and incident beam 3 will be equal to 2 pi into h, which is the index of the H00 plane. So magnitude of the H00 plane index, and use the fractional coordinate of this atom, fractional lattice coordinate. You can understand it as x by a. If a is the lattice parameter, then x is the distance between this atom, which is at fractional coordinate, and this atom, which you can consider as being at origin. So 2 pi hu will be the phase difference. If u is equal to 1, then it will be 2 pi h, which will be an integer. So this will lead to a part difference, which will be a multiple of lambda, because we know that a 2 pi phase difference, this is important to know that a 2 pi phase difference corresponds to a path difference of lambda. So using this we can know the phase difference between diffraction that occurs by different planes of atoms, and then when we look at all these planes in a particular unit cell, we can tell what will be the intensity of diffracted beam by a whole of a unit cell. I think that will be covered in the subsequent lectures, but with this we have done the recap of module 10. If there are any questions you can let me know, else we can take a short break and then move to the assignment. These are some questions you can answer after this session. This is the assignment. If there are no questions, let's take a 5 to 10 minute break, a 10-minute break, and then we'll start with the assignment at 4:10 p.m. Hello. So let us start with the assignment. I hope my audio is fine now. Let me know if you are facing any issue.
Yeah. Yes.
So let's start with uh, discussion on the assignment.
Sir, your voice is not audible,
You
sir.
all can hear me well now.
Not clear, sir. Till also.
Mutyalu, are you trying to speak? I can't hear you.
Yeah. I no not speak, sir. But your voice is not
Wait,
clarity.
wait.
That
I think there is a issue with my audio.
maybe sir. Correct.
Yeah. My there was a issue with my audio. Now I can hear you. Yeah. So should we start with the assignment?
Yeah.
Okay. So let's look at the first question. Mosley's law describes the relationship between. If any of you have any idea what the answer is, you can let me know. You can just unmute and tell, or what your guess is. So, um, okay, let's discuss this question. So, what does Mosley's law tell? It tells the relationship between the uh, the relationship between the frequency of X-ray that is uh, emitted by an atom of atomic number Z, and this corresponds to the mm, absorption edge or the characteristic X-ray. We can also go to the concerned slide where this is discussed. Yeah. Mm. Let's go back and look at the options. So here you have frequency of absorption edge and the atomic number of the absorber, wavelength of the characteristic emission line and the atomic number of the emitter, critical excitation voltage and the atomic number of the target material. Mm. So we know that it describes the relationship between the atomic number of the material Z and the absorption edge for that material. That is the wavelength at which we will see the absorption edge in the mass absorption plot, mass absorption scattering versus lambda plot. Uh, Basically, what it means is that we will require a X-ray of this frequency in order to remove electrons from the inner shell. For example, it could be the K shell, which is the first shell. So I think this is the most accurate option, which describes Mosley's law. The frequency of absorption is and the atomic number of the absorption of the absorber. But this will also be related to the wavelength of the X-ray which will be emitted due to de-excitation of the atom, and also it will be related to the critical excitation voltage of the target material. So from the target material we are getting the incident X-ray beam which is hitting your specimen, and once it is hitting the specimen, it is leading to the creation or the formation of the absorption edge. So your specimen is basically absorbing a part of the incident X-rays, and at the absorption edge wavelength, it is absorbing a lot of X-ray, a lot of the incident beam. So these two options are also correct in a way because they are related to Mosley's law only. But so I think D can also be the correct option. I hope that this question is understood by you all now. If you have any doubts, you can let me know. Okay, let's go to the next question. Two X-ray tubes have identical targets, but tube A operates at a voltage just below the critical excitation voltage. You can take some time to read the question, and then if you have any guesses, you can let me know. Also, in case the previous question's explanation was not uh, satisfactory, I can just show it by a diagram to make it easier to understand. Because, for example, if you have a X-ray tube here, you have a target material. There are electrons which are impinging on this material. So this X-ray tube is at a uh, accelerating voltage of V, let's say. So electrons are impinging on this target material. X-ray beam is getting generated as a result. This X-ray beam is then hitting some other material, which is, let's say, the absorber. And when it is hitting the absorber, some part is, let's say, this is sitting like this. Some part of it is getting transmitted while some part is getting absorbed. So here the first option is related to the uh, absorption edge mu by rho. So the absorption edge will be something like this. So Mosley's law will tell you at what particular lambda, let's say this is lambda naught, what particular lambda we'll have the absorption edge, and that will be given by root of mu. Let's say this is mu naught equal to C into Z minus sigma. But also the wavelength of the characteristic emission line of the emitter, that is the wavelength of the, so there will be some amount of some X-ray which will get transmitted, but some X-ray will also get emitted, which will have a different wavelength. So we can just show it by this. If this is the emitted X-ray, it can be the characteristic X-ray for this absorber material, and this will be related to the atomic number of the material. So because it is probably some characteristic X-ray, and this atomic number of the material is related to the absorption edge frequency. Now the third option tells about the critical excitation voltage and the atomic number of the target material. So uh, here here also we know that the target material will only emit X-rays when the energy of the impinging electrons is above a certain value. So that is, the energy of the electrons should be enough to knock out the inner electrons so that characteristic X-rays can get emitted. And this will be related to actually the Z value of the target material. So in a sense, the X-ray getting energy of X-ray getting emitted will depend on the Z value of target variable and the energy of the electrons impinging. But I think the most correct answer is A. So I think we can go with A instead of all of the above. Now I hope this question was clear to you. It's an important question because it discussed many different things. Now let's go to question 2. If any of you have any answers, you can let me know, or else I'll discuss. Tube X-ray, two X-ray tubes have identical targets. Uh, Tube A operates at just below critical excitation voltage for the K series, while tube B is just above Vk. What is true about the X-ray spectra produced by the two tubes? So if the critical excitation voltage is less than the K series, that of the K series, then we know that the electrons which are being accelerated by this voltage, when they interact with the specimen, they will not have enough energy to remove the electrons from the K shell of the target material, and as a result we will not see any characteristic lines which will be associated with the K shell, for example K alpha or K beta. But in case of tube B, we will see this characteristic K alpha comma K beta lines. So we might see other lines, but K alpha and K beta are the most characteristic lines for any material. So we can say that only B will produce characteristic lines. If this is clear, we'll go to the next question. Which of the following statements about X-ray filter is false? So we have already discussed this in the recap of the lecture. If any of you know the answer, you can let me know. The correct answer to this will be B. When we are using a filter, we usually use one which has a absorption edge which is between K alpha and K beta of the target material. And now I have shown here that what is the target material and what is the absorber material or the specimen which you are using. So in this case, it is the filter material. So we know that this should be true. Also, increasing the filter thickness will lead to a decrease in the K beta by K alpha intensity ratio, because more of the K beta, it is more likely that the K beta beam wavelength, K beta wavelength beam will get absorbed if the filter thickness is increasing. So this ratio will decrease, and then filters are made of atomic materials with atomic number one less than the target. So this is also true. But a filter can completely eliminate the K beta line from transmitted beam. This is not true, because some of the K beta intensity, the some of the K beta beam will still get transmitted through the material. It might not get absorbed completely. So there will still be some amount of K beta in the transmitted beam. Coming to question 4. Here we have a copper target. What should be the suitable material for the filter? Any uh, any idea what the answer could be? So as I discussed in the previous question, the filter material should have atomic number, which is usually it is always lower than that of the target material, but usually it is lower by one atomic number. So here, if the target is equal to 29, then it is probable that using something like is equal to 28 will lead to uh, a decrease in the K beta wavelength which we desire. So this will be the most suitable filter material. Also, if you want to know why we use filter material when an atomic number one less than the target, I can explain it. Let me know. Mm, okay. So let's go to the fifth question. We have a X-ray tube with a molybdenum target, which is operated below the K excitation voltage. The resulting X-ray spectrum will contain Hmm. Any idea what the answer will be? I hope you all are able to understand the contents of this module that we are covering. In case you are having doubts, do let me know. We can discuss on it. I'll suggest that you all go through the lecture videos so that you'll be more confident about all of these concepts. The answer to this will be C, because the voltage at which the X-ray tube is operating is less than the K excitation voltage. So electrons from the K shell will not get knocked out. As a result, there will not be any possibility of K alpha or K beta lines, since for these you need to have a vacancy in the K shell. So we will not see these characteristic lines. We'll only see a continuous spectrum. Question 6. Two different powders A and B are analyzed using X-ray diffraction. A is finely ground and B consists of coarse, larger, coarser grains. So which of the following statements is true? Hmm. So here we wish to know what kind of diffraction pattern we'll see for two powders having different sizes. A is finely ground and powder B has large coarse grains. I think the answer should be B. But this question is a bit ambiguous, I feel, because here it is not show how the here we are being told that powder B has large and coarse grains, but we don't know what is the size of the grains in powder A. It is just said that A is finely ground, so the particle size of the powder is smaller than B. Hmm. But okay, if we assume that the powders, just the size of the powders is different, but the internal microstructure of the powders are the same, then we know that X-ray diffraction has to do with the atomic spacing between with the spacing between the atoms and the atomic planes. It doesn't matter how big the particles are. So there should not be any difference in the diffraction patterns, any significant difference. So the answer will be C. Hmm. So question 7. What does the Thomson equation describe? So here we have X-rays which are scattered by single electrons on interaction with the incident X-ray photon. And this will should depend on, I think, all of these, you can look at the formula to know the exact relationship between all of these and the scattered X-ray beam intensity. So we know that since the incident X-ray photon is basically an electromagnetic radiation, there is an electrical and magnetic field which is oscillating. So as a result, the charge of the electron will play an important role, since the electric field will lead to a force on the electron, which will cause the electron also to oscillate. So charge is important. The mass is also important, because how much the electron will oscillate will depend on the mass of the electron. The force will depend on the charge, but the displacement of the atom will be dependent on the mass, or the acceleration of the atom will be dependent on the mass, F equal to ma. Then the distance from the electron will also matter, because as the distance of as the position at which we are measuring the intensity of scattered beam is moved away from the electron, the intensity of the scattered beam will decrease. So it will be proportional to 1 by r square. As you move away, as r becomes higher, the intensity will decrease. Now this will cause a decrease. So the answer will be D, all the above. The polarization factor in Thomson equation arises because the correct option will be T. The incident X-ray beam is unpolarized. So unpolarized means that the electrical and magnetic fields in the incident X-ray beam are oscillating in at all different random planes. So at multiple planes, the oscillation is occurring, and as a result, the electrons which are interacting with the X-ray beam will also oscillate in multiple directions, because of which we'll see scattering in all directions. And this will lead to uh, change in the intensity at different scattering angles. But if it is an unpolarized beam, sorry, if it is a polarized beam, then the incident X-ray beam, electromagnetic radiation, for I should say the electrical and magnetic fields, they will only be oscillating in one single plane. So the scattering by the electron will also oscillate in a single plane only, and as a result, the scattering will probably only be in one direction only. So we will not need any polarization factor. Hmm. I think this should be somewhat correct, the explanation I gave. Now, question 9. Quantum scattering is characterized by. We discussed this multiple times during the recap. The answer will be an increase in the wavelength of scattered radiation. So the energy of the scattered beam is lower than that of the incident beam, which means that the wavelength of the scattered beam is higher. Question 10. The atomic scattering factor for an atom with Z electrons is equal to Z when the answer to this will be C. We have discussed that for forward scattering, we'll have uh, no, we can for forward scattering, we can directly add the amplitudes of scattering by all the electrons because there is no phase difference. So the scattering factor is 1. Sorry, the scattering factor is Z, else it would be lower than Z. Question 11. Two atoms uh, have the same atomic number. A is uh, A has electrons more tightly bound to nucleus than B. Which atom will have a higher atomic scattering factor at a given non-zero scattering angle? So this is a, I think, hypothetical situation where in one case you have electrons more tightly bound to the nuclei than the other for the same atomic number, and the angle of scattering is also the same. How will the atomic scattering factor be affected? We know that the atomic scattering factor is dependent on the angle at which the scattering is taking place. And if the angle is 0, we have it equal to value Z. Let's go to the concern slides to get a better understanding. Mm. So this is a good question that was asked. Okay. So we have the atomic number same. The electrons in one case are more tightly bound than in the other case. The angle is the same. So we know that atomic scattering factor basically uh, is related to the phase difference that comes due to the scattered difference that comes because of the path difference between the scattered beam from multiple different electrons. But in this case, if the electrons are more tightly bound to the nucleus, then you can maybe say that the path difference that will come between between the scattered beam from different electrons will be smaller in case of A than in case of B. Again, this is a hypothetical situation, so this is just a hypothetical answer. So if the part difference in case of A is less than that in case of B, it is likely that the phase difference will also be smaller due to the smaller part difference, and that will result in a higher atomic scattering factor in A than in B, since it is less likely that you will have uh, phase differences of maybe 90 degrees at or 180 degrees. So at 180 degree phase difference, you can have in a destructive interference. There will be no intensity, and at 90 degree, uh, so if the phase difference is less, then then we can say that the overall uh, scattered beam will have a higher intensity, since there will be more of constructive interference. So the answer should be A. I hope this was clear. This was a bit of a tricky question. Now let's go to question 12. X has a higher atomic number than Y. Which of the statements is true about the scattering behavior? A. At all scattering angles, X will have a higher unmodified scattering intensity. We know that the atomic scattering factor will be equal to Z at theta equal to 0 degrees. And so from that we can say that a higher atomic number will always correspond to a higher atomic scattering factor. So I think A should be correct. But let's also look at the other options. So X has a higher atomic. Okay, so here we are talking about the scattering intensity, not the atomic scattering factor. So we can't directly say that X will have a higher unmodified scattering intensity than Y. We can say the atomic scattering factor will be higher, but we can't directly comment on the scattering intensity. But if we see this option, we know that Y is a lighter element, so the Compton scattering modified scattering intensity will be higher for Y than for X, because at lower atomic numbers, Compton effect is more. So I think the answer should be B. Let's just go to this part in the slides. Yeah, the answer will be B. Let's move to question 13. Which scenario would result in the most significant decrease in F for a given atom? Decreasing the scattering angle while keeping the wavelength constant, decreasing the wavelength while keeping the scattering angle constant, increasing the atomic number of the atom, and shifting the electron distribution further away from the nucleus. So if we have this kind of plot, decreasing the wavelength will cause a decrease in the atomic scattering factor, yes. Decreasing the scattering angle will lead to an increase in the actually atomic scattering factor. As you decrease the scattering, it will scattering angle, the F value will increase. Increasing the atomic number should not have a very significant effect on F. Actually, it will increase F because the Z value is higher. So F will also increase by some amount. So this will increase and shifting the electron distribution further away from the nucleus. If electrons are further away, then it is possible that the phase difference between the scattered beam from different electrons will be higher. So atomic scattering factor can decrease. But I think decrease of wavelength will have a direct effect on the atomic scattering factor. So this will lead to the most significant decrease in F. The answer should be B. This was also covered in the lecture. Because the wavelength also has an effect on the phase difference. Since for the same part difference, you have a smaller wavelength, which will lead to a higher phase difference. Question 14. We have two X-rays having part difference of lambda by 2. Their phase difference is, so 2 pi I have told 2 pi phase difference corresponds to a part difference of lambda, one wavelength. So lambda by 2 should correspond to a pi radian phase difference. Answer is B. Question 15. X-ray beam falls to 40% of the initial value after penetrating a target material of 1 centimeter thickness. Find the linear absorption coefficient of the target material. So here we can see that 60% of the incident beam is getting absorbed. And we know that I transmitted is equal to I naught e raised to minus mu by rho into I think x. So as the mass absorption coefficient increases, the transmitted beam intensity decreases. Let's look at the exact formula. Hmm. So here's the formula for absorption of X-ray beam. We need to know the linear absorption coefficient, which is given by mu. So yeah, here you have minus mu by rho into x into rho again. And mu is our linear absorption coefficient. So IT by I naught is 40% we know. 0.4 equal to e raised to minus mu into x, where x is 1 centimeter. So ln of 0.4 equal to mu into 10 raised to minus 2 meters, which implies mu equal to minus of ln of 0.4 divided by 10 raised to minus 2 meter inverse, which is equal to 0.916 meter inverse. So our answer is 0.916 meter inverse. With this, the assignment is complete. In case there are any doubts, you can let me know. Okay, if there are any, if everything is fine, there are no doubts, we'll wrap up the session now. And I'll meet you again in the next session on Saturday, where we'll discuss on module 11, which will also be related to X-ray diffraction. Thank you.